Good morning, everybody. Where'd everybody go? Thursday. What test?
No, I just said they were sick.
Oh, yeah, everybody's sick. Everybody has the flu. Sometimes it's either a train, but now I'm in a new building where the train doesn't get in the way so much. And then the other time is there's usually like a math test or an organic chemistry test or something that clears people out. If you're listening to this and you weren't here on YouTube, so this is none of you in the room, get here on time. It's worth it. All right, we were here, and we are going to delve into this work other term that's sitting here off to the side, and we're going to define work. We're going to praise work because it's the way that we get rid of vectors, and then we're going to start applying it to our conservation of energy situation. So this is rather unfortunate, isn't it? I mean, obviously. My question is, are they holding it up, like keeping it from rolling down the hill, right? Are they pushing it up the hill, right? Or are they slowly bringing it back down there? Hopefully they're trying to push it up the hill, but that seems kind of impossible given the circumstances, yes. But why do I have this picture? Work. As soon as I say that word, I'm sure there's all kinds of negative connotations that jump into your mind, right? Because it's the thing that we do, right, in endless circles. We go to work so that we can pay the bills, so that we can go to work again, so that we can pay the bills, and over and over again. So it's not that kind of work we're talking about, obviously. It's mechanical work. And for mechanical work to happen, there must be motion. Mechanical work can't be happening without an object moving somewhere. So if these people are just holding up this car, in other words, if they're keeping it still, how much mechanical work are they doing? Zero, which is kind of weird, isn't it? Because you're like, well, you get tired. Okay, so I can lean here against the wall, right? Am I doing any mechanical work? Why not? Wait a second. Can we now say with confidence that there's no work because it's not moving? Yes, right? That was always the problem with Newton's second law, was it? Acceleration is kind of this weird thing. Not only is it moving or not moving, but I got to know how it's going to change that motion, right? That's kind of a difficult concept to get into our brains. But now we're back to actual just moving or not. And if I'm just leaning here, I'm not moving. And so no mechanical work is being done. Biological work is being done. There's stress in my muscles, right, and all that kind of stuff. And so energy in a biological sense is being used, right? But as far as mechanical work taking place, there isn't any. All right, I'm going to go rescue the recycled bin. I'll be right back. Looks like they managed to unlock the door. Okay, so let's delve into how we're going to mathematically express our work, okay? Work as I'm going to just toss the definition at you. A little bit of a simpler definition than you might see in your book, and we might get to the big one later, okay? But you'll note, okay, so first of all, I think your book uses the symbol S. A lot of people use the symbol S as a generic distance. It's not just X, it's not just Y. It can be really in any direction. But notice how work, vector, scalar, or elephant? What? How do you know it's a scalar? There's no vector sign over the top, right? I didn't write the vector sign over the top. So that must mean that work is just a number. It doesn't have like direction associated with it, which is like, oh, thank goodness, right? But notice force and displacement, force and this s vector, right? This generic distance vector. We'll change that to an x or a y or something like that, right? But like those two things are vectors, right? So we are now multiplying two vectors together and getting a scalar out. This is called the dot product. And I'm going to teach you about the dot product, okay, in a bit of nauseating detail, okay? But before we do that, I just want to give you an idea of what it's like to kind of multiply two vectors together and not get anything out, okay? And specifically, we can see in this definition that if there is no distance s, right? If we're not going anywhere, we're multiplying by 0, no work is being done. Okay, the units here. Let's just quickly talk about units. What are the units of force? It's a Newton. What's the unit of distance? Meters, right? So a Newton times a meter, we're going to redefine, we're going to call this a joule. Not like a diamond or a ruby, that kind of jewel, but James Prescott jewel, last name of somebody. So Joule. The symbol is just a capital J. Now, this unit is probably something that you are not familiar with, okay? We don't run around talking about joules all the time. As a matter of fact, we really don't talk about energy all that often in common, everyday society. We'll talk about power. We'll get to that at the end, about horsepower, that sort of thing. Energy, probably the closest energy unit that you're familiar with is the kilowatt hour, which is what shows up on your electricity bill, if you've ever seen that, okay? That's a unit of energy, but it's not like in the SI units so much. Well, it sort of is. The hours mess it up a little bit. But let's just to give you an idea, right, of kind of how big a joule is. Again, this will be a unit that you'll never quite be familiar. Even somebody tells me how many joules of energy are in something, I go, is that a lot? Is that a little? I have to go look it up. So the act of turning a page, this requires work. And how do you know it requires work? I'm moving something, right? There's motion here, right? Okay. I'm applying a force and it's causing the page to move. That's approximately a millijoule, so 1/1000th of a joule, right? You have to turn 1,000 pages to get to a joule, okay? A car moving at 60 miles an hour has about 800,000 joules, right? So that's kind of a big range, right? Little tiny bit of work being done versus a lot of work being done, right? To get that car to get up to speed. Your heartbeat, okay, is taking about a joule. The bulb, like a light bulb in your house, if it's an LED light bulb, is using about 8 to 10 joules per second to generate that light, okay? So it can be hard to sort of get a feel for the scale here, right? But we live in an everyday world where we have objects that have hundreds of thousands of joules and other things that are millijoules, right, worth of work being done. So it's a big range. And for those of you that are counting, the total U.S. energy use in 2013, I need to update my statistic apparently, was 10 to the 20 joules. You add together gasoline consumed, electricity, right, all that kind of stuff, you put it all together. 10 to the 20. That's almost a trillion, right? Like joules worth of energy. All right, so let me demonstrate something. Okay, so I have a tennis ball, right? Okay, and if I'm just holding this tennis ball right here, is any mechanical work being done? None whatsoever, right? Okay. But if I push the ball up, am I doing work? Sure, right? Okay. All right, if I'm holding the ball up and lowering it down, am I doing any work? Yes or no? Why are you wondering? You're like, there's got to be a trick in there, Mr. Balogh, right? You did up, and now you're doing down, and I know I'm going to be wrong, and I hate being wrong. I'm always wrong. Okay. I'm not talking about force of gravity yet. I'm just talking about the work that my hand is doing on the ball, right? Okay. So you agree that I'm doing work if I push the ball up, right? Which way is the force? Up. Which way is the direction? Up. Okay. As I lower the ball, which way is the force on the ball from my hand? It's still up. Am I pushing the ball down? No, right? I'm like, right? Okay, no, I'm not doing that, right? I'm still holding the ball up, right? But why is it going down? Gravity is winning, right? Okay. There is a force of gravity here pulling the ball down, right? But the ball, the normal force on the ball is still up, right? I'm pushing up on the ball. It's just that the distance this thing is moving is backwards, isn't it? Okay. So there's a difference between those two works. The work of pushing the ball up, where the force is up and the displacement is up, is known as positive work. But if I'm lowering the ball down, my force is still up, but the direction this thing is going is down, that's negative work. How much work is being done now by my hand? If moving up is positive and moving down is negative, what do you think moving sideways might be? It's 0. What? This is nuts. Hold on. My force is this way, isn't it? My hand holding the ball up is perfectly vertically upwards, right? Which way is the ball going? Sideways. Those are perpendicular things. That force is doing nothing to help the sideways motion. All right, let's screw up your brain a little bit more before we get into the math. If I drop the ball, and let's talk about the force of gravity now, okay? What direction is the force of gravity on the ball? It's down, right? Which way is the ball going? Down. What kind of work is that? Positive or negative or 0? Negative. It's positive work. It's okay, right? Why is it positive work? The force and the direction are the same, right? Okay. What if I throw the ball up in the air, right? As the ball is on its way up, gravity is doing what kind of work? Positive or negative? Negative. What direction is gravity? Down. Which way is the ball going? Up. So gravity does negative work on the ball as it's going up until it hits the top. And then what kind of work does gravity do as the ball falls? Positive or negative? Positive. So it goes from negative work to positive work. Yes? How is this different from kinematics? You're about to see. So, notice with negative work, what happened to the speed of the ball? It slowed down, didn't it? Okay. And what happened to the speed of the ball as positive work was done? Sped up. Okay. Well, accelerated in both cases, right? All right. So we've got to kind of untangle all of these ideas, right? And the way we're going to do it is in this multiplication called the dot product right here. So let's talk about the dot product mathematically, what it is, and then we'll circle back around and we'll get back to why we're using the dot product to describe this quantity called work with its strange positive, negative, 0 kind of thing going on. Okay? So the dot product between two vectors, we already saw one of its effects, right? That when you take this dot product, right, you don't get a vector. Right? You get a number. But what is that number telling you? How many of you have encountered dot product in math classes? Yeah, okay. So half of you. The rest of you, don't worry about it. You are pure and clean and haven't been affected by the mathematicians. The dot product answers a question. The question the dot product answers is, how much of one vector points in the same direction as another? Vector A. How much does vector A point in the same direction as vector B, and vice versa? And the answer, positive, negative, or 0, is really indicative of, well, are the vectors parallel? Perfectly parallel vectors will be positive, right? If you have any amount of a vector that's pointing in the same direction as another, you're going to get a kind of positive answer. But if there is an opposition between two vectors, right? If they're pointed in opposite directions or any part of another vector is opposite the other one, you'll get a negative sign, a negative dot product. And what do you know about vectors if you get 0? They're perpendicular to each other. Guaranteed. If you take the dot product between two vectors and you get 0, then those two vectors are guaranteed to be perpendicular to each other. So that's a powerful idea. How are we going to pull it off? Okay? So just to review, right? If two vectors, right, have the same direction, a dot product is going to give you a positive result. Okay? If two vectors are opposite each other, you're going to get a negative result. And if two vectors are perpendicular to each other, you're going to get 0. Okay? All right, so how does this magic happen? There's two ways to calculate a dot product. Okay? One way is if you know the magnitudes of your two vectors. You multiply. You just right? It's a multiplication, right? And so you just multiply the two magnitudes together. Notice there's no vector symbols over that A and B, right? You just multiply the two magnitudes together, but you also need to take the cosine of the angle between the two vectors. So that can get a little bit tricksy, right? So let's say you have a vector A like that and a vector, oh, that was too perpendicular, a vector B like this, okay? A might be, at 60 degrees, and B might be at 80 degrees, right, from the x-axis. But neither of those angles goes into this calculation, right? If A were at, 60? And B were at 80 degrees, what angle would you put into the dot product calculation? 20. You'd put 20 in. The angle between the two vectors, right here, okay, would be 20 degrees. And again, that can be kind of tricky, especially if you've got vectors that are pointing like way opposite each other, right? Do I use 190 or do I use the other one, right? It can get a little bit zany, and in physics, we really only use this method of calculating a dot product if we're forced into it. That's not true. It depends on the situation, I guess, is the answer. Let's do the other form of the dot product. It's a multiplication, right? So if we have, I'm going to do this the most general way possible, just so you can kind of see, and then we'll do some numbers, okay? So let's say we have a vector A, and it's AXI hat plus AYJ hat. We'll just do two dimensions. And we've got another vector, and it's got its component x and its component y, right? I'm using just generic symbols for this, right? We're doing a multiplication, right? So let's just multiply these things together. Let's go for it, right? So what happens? That's going to be AXI plus AYJ. You really don't have to write down the intermediates here. Write down the punchline if you're going to write anything down. BXI plus BYJ. Okay, so all I've done is I've taken the two vectors, multiplied them together, right? So here we've got two things, two terms. You know what to do, right? What do you do? You foil? Right? So, what does that look like? Okay, this is going to get ugly. what is that going to be? AX BX I times I. I pulled everything that's a number. I grouped the numbers together, and then I grouped the vector parts together, right? Okay. And then the next term is going to be AXBY I dot J, followed by AYBXJ dot I. I'm not dealing with this multiplication of vector directions yet. Plus, what is this? AYBYJ dot J. So that, if I foiled that correctly, which I always thought was kind of hilarious when you think about it, foiled again. All right, what have I, okay. Oh dear. What is I hat? Like what's I hat? Do I need to go get my hat? It's a unit vector. And the term unit vector, what does the word unit mean? It's the magnitude, right? It's got a magnitude of 1, right? The term unit in mathematics means 1. So the I vector, I hat vector, has a length of 1, and what is its direction? Positive x, right? It lies along the x-axis. So let's take a look at what I dot I would be, right? That's what we're trying to suss out here. And I told you what the dot product does, right? I told you that it asks a question. How much of one vector points in the same direction as the other, okay? Well, what's the answer for I dot I? It's 1, right? Like a 100% of the unit vector I hat points in the same direction as the unit vector I hat. So whenever you see two unit vectors dotted together, the answer is 1. But what happens if we ask the question, how much of I hat points in the same direction as j hat? The answer is 0. How do you know that? They're perpendicular to each other by definition, right? X and y axes are perpendicular to each other. So moral of the story here is, if you end up with a multiplication that's got two vectors pointing in exactly the same direction, you're going to get 1. Two unit vectors pointing in the same direction, you're going to get 1. And if they are any other combination of unit vectors, what's the answer? 0. So what's I dot k? 0. What's j dot k? What's k dot I? They're all 0, right? You're asking a question. How much of x points in z? Well, none of it, okay? But if you get k dot k, what's the answer? 1. If you get j dot j, getting the idea? Okay. So what does that mean for our big FOIL here? What's this first term going to end up being? I dot I is 1. So this is just ax bx, isn't it? What's I dot j? It's 0. What's j dot I? 0. And so we're only left with ay by, and what's j dot j? It's just 1. Here, I'll put the 1s in, just so you know that they went to 1, right? So in the end, we see, a y b y. We see another way for calculating a dot product. If we know the components, then what do we do with the x components? We multiply them together. What do we do with the y components? We multiply them together. And then when we've got those two things done, what do? Add those two results together, and you get a what? A number, a scalar, right? With no, are there any directions in this box? None. Right? Lucky for us, all the negative signs are going to work themselves out too. For example, right? What if we had I dot negative j? I dot negative I. It would be a negative 1. That minus sign carries through, right? So the dot product knows how to deal with it, right? If in here, like by were a negative 3, right? It would know how to work that out. Okay? So two boxes on the screen, two ways of dealing with a dot product. One way if you're given magnitude and angles, right, you can find the dot product. This way, if you know the components of the vector, you can get the dot product that way. Those two things will end up giving you the same number. So let's do an example. I'm just going to do the component example here. So by way of example, A is going to be, I can't even read my writing, 3i hat plus 6j hat. We could have just made numbers up, right? B we'll do as 4i hat minus 1j hat. Yeah, okay. So let's find the dot product. What are we going to do? We don't know the magnitudes. We don't know the angles. So we're going to use the second box, right? What's the first number I write down? What's AX? It's 3. What's the next number I write down? 4. Why do I write down 3 times 4? I'm doing AX times BX. I take the X components and I multiply them together. All right? And then I'm going to add on, what's the next number I write? 6, and then multiplied by -1. I look at it and I go 3 times 4, and I start to panic because I can't remember my times tables. Is that 12? 12 minus 6. Where'd the minus sign come from? It's plus a minus 6. And the last time I checked, that is 6, right? Whatever that means, 6, right, okay, is what it means. But not only have we just found the dot product between these two vectors, it's positive, by the way, which means that they had to be somewhat parallel to each other. Not completely, but somewhat parallel to each other. Now that we've got that, we can actually find the angle between these two vectors. How do we find the angle between these two vectors if we know the dot product? It's up here, right? What is A dot B? It's 6, right? So if I come over here and I say 6 is equal to the magnitude of A times the magnitude of B times the cosine of the angle between them, then the way I'm going to go find that angle is I need to find the magnitude of A. And then find the magnitude of B, and then I'm home free. So how do I find the magnitude of A? Pythagorean theorem, right? Okay. Square root of 3 squared plus 6 squared. I got 6.7. Magnitude of B. It's going to be the square root of 4 squared plus 1 squared. I got 4.123. So there's my magnitudes of my two vectors, right? So now I come over here. 6 is equal to 6.7 times 4.123 times the cosine of theta. So 6 over these numbers, I don't even really care what they are, 3 equals the cosine of theta. And how do I get that theta all by itself? Inverse cosine. And 6, oh, I got a 27.7 on the bottom, gets me 77.5 degrees. So whatever angles they are, I know that the angle between them is that number, right? Okay. And so they weren't, 77 degrees, 78 degrees, that's not very parallel, right? But we did get a positive answer, meaning that it was a part of A was pointing in the same direction as the part of B, which could be useful information depending on the problem that we've got. Okay, so there's our tour. Maybe your first eyeballs on this concept and idea called a dot product. It's a way of multiplying vectors together so that we get a number, a scalar back out. And that number is telling us something about how parallel or anti-parallel or perpendicular two vectors might be. There is a spoiler alert, there is another way to multiply vectors together. 2 ways to multiply vectors, okay? We only have 1 way to multiply when it comes to numbers, but there's 2 ways for vectors. What's the second way? Cross product. Now the reason the dot product is called the dot product is we use that symbol the dot symbol between the two vectors, right, for multiplication. The cross product uses that x multiply symbol, okay, between them. The cross product, which we'll get to later. So by the way, if you want to know more about dot product and how to do it, it's in chapter 3. Remember chapter 3, we cut out half the chapter? The other half was the dot product and the cross product, right? So you don't need to know more than what I've got on the screen, okay? But if you need a reference, it's there. The cross product gives you another vector. That's the magic of the cross product, okay? So one way of multiplication gets us a scalar. The other way gets us a vector. It's natural to ask, well, why would I ever want to get another vector out? I don't like vectors, Mr. Balogh. They've ruined my life. And I'm with you, right? But sometimes we do need that vector back out. Okay, so where were we? So I showed you the dot product, right? And we saw how work right here, right, was a force dot product into a direction, right? So let's do a little bit of kind of conceptual what if, okay? And let me draw, let's say we've got a wagon. Wagons are great. I like wagons. Wagons are fun, right? And a kid is pulling their wagon across the ground. I haven't, of course, drawn the wheels or anything. It's a wagon. You can tell because it's a wagon. Okay. And usually when you're walking with the wagon or something like that, you're not pulling, you're like pulling up at an angle, right? It's not like you're down here pulling straight and you're not pulling straight up, right? You're pulling at some sort of angle, right? So there's a force, right, of the pull, okay, coming through the handle of the wagon. Well, that's not the only force that's acting on the wagon. What are some other forces that are acting on the wagon? Okay, so there's normal force, right? We're in contact with the ground. The earth, gravity, okay. Love it. Weight. And then some sort of resistance, right? Okay. Friction from the air, friction from the wheels. We'll just lump all the friction together because we don't want to get into too much detail there. So we could ask about the total work being done on the wagon. Like, what is if we find all the individual works and add them all up, what would it be? We could ask that question. We could also ask, how much work is an individual force doing? Okay? So we're going to ask all of those questions. So let's tackle the easy ones first. What's the work done by the normal? Oh, by the way, the wagon is going which way? Yeah. It is going this way, right? So it's displacing to the right a distance delta x. Okay, so how much work is the normal force doing? If you thought that long, something's wrong. It's 0. Why is it 0? Which way is the normal force pointing? Up. Which way is the wagon going? To the right. Those are perpendicular things, aren't they? So what's the work done by the normal force? It's 0. You want to find another one that's 0? The work done by the weight, right? Work done by gravity? Also 0, right? Those forces and those distances are perpendicular. We could find the dot product, right? It would be magnitude of n times j times delta x times I. What's j dot I? 0. Doesn't matter what the numbers were. J dot I is 0. We get 0. Okay, so those two are 0. Work done by the friction. Careful. It's a negative number, whatever it is, right? Why is it going to be a negative number? It's opposite, right? We're going to get a negative one out of there. But basically, it would be the magnitude of the friction times the magnitude of delta x, right? And then the friction is negative I hat, and the delta x was Mr. Balogh, you're such a terrible teacher. Let's do it this way. F negative I hat times delta x I hat, right? And if I move the numbers and then just get the vector things together, what's negative I dot I? It's negative 1, okay? So this is negative F delta X, right? And so why would the friction be doing negative work? Like, what does friction do? It resists, right? It acts against things. And this is what kind of friction, kinetic or static? It's kinetic. I know it's static between the wheels and the ground. That's different, okay? But like that resistive force is trying to slow the wagon down, okay? That's kinetic friction. Kinetic friction always does negative work. Always. Static friction, it depends. Okay, we'll get to static friction in a bit. Static friction is not going to show up in energy because we hide static friction in our energy terms. But if you see friction in a problem and we're doing work energy, guaranteed that friction is doing negative work. All right, you have very few guarantees in this class. That's one of them. All right, what about the work done by the pulling force? It's positive work. It's not like 100% positive work, right? So there's different ways we can go about doing this, right? We could do F times delta X, F delta X cosine of like whatever angle we're holding this thing at, right? Okay, cosine of theta, that's one way to do it, right? Okay, we could go find what that vector F's components are, and the delta X components are pretty easy, right? Okay, so F has I and j hat components, doesn't it? Like magnitude in the x direction, magnitude in the y. But what does delta X have? What are its components? It's just X. It's just I hat, right? So when you pull off this cross product, no matter what the numbers are in front of the I's and J's for the S, what's the only one that like survives? It's just the X component, isn't it? Because you're going to get another multiplication that's I dot j, and I dot j is 0, isn't it? So this turns out to be Fx times delta X. Right? The component of the force that only points in the x direction. In other words, there's a component of F in the x direction. There's a component of F in the y direction. And the component of F in the y direction does how much work? 0. Because it's trying to move the wagon upwards, but the wagon is moving sideways. Right? So it would be another 0, and the only thing that would survive would be Fx, and that work would be Fx times delta X. So lots of different ways to think about the same thing. Usually what I do is I go, okay, delta X, I just need components in that direction, whatever it is. One of the dangers of this definition right here, this is a warning to you, okay? While strictly true, it's AB cosine theta, okay? Be careful about that angle. Remember I told you it's the angle between the vectors, right? Okay. When we are looking for components of vectors, what trig function would we use to find Fy? If our angle theta is right here, we're looking for that one, and it's not touching the angle, sine. So if we wanted to find the work, it would be Fy, it would be F sine theta times delta X, right? This would have a j hat. This would have an I hat. And now you're looking at this going, Mr. Balogh, that says F delta X sine theta. What happened here? This cosine theta is the angle between the vectors. It's not a component, right, of vectors. And so sometimes students get really messed up. They're like, wait a second, why am I using sine all of a sudden? It's because you're dealing with a component of a force. And you're no longer doing angle between things. Okay? By the way, I wrote it correctly here, cosine theta. Since this is x and this is the force, what's the angle between them? All right. Just so you're aware. Just so you're aware. Okay. The big ugly that I am saving you from, okay, has to do with the fact that work, strictly speaking, isn't as easy as I said it was. What?
So if the block was going up, would it be a sine?
Of that angle? Yes.
Yeah. Okay.
Yeah. If it was moving in the y direction, certainly. So the thing about work is it's actually the integral of the force over some path. Not all work is done in just one direction, okay? And so while this, well, here, let me write it a different way. I won't use L. Let's get rid of the L. That was more generic than it needed to be. You can do it in the x direction, you can do it in the y direction, you can do it in the z direction, okay? But if we move something and the force changes. So in all the examples I did previous to this, the force was constant, right? It wasn't changing at every point, right? It was exactly the same. But if our force changes, if you're pulling the kid in the wagon and you like tug a little bit and then you tug a lot, right? In order to find the total work, we'd have to know each individual little piece of force as it pulled it over a little tiny distance. And if we take all those little tiny distances and we smash them up really, really tiny, and we add them all up together, what are we doing? We're integrating, okay? Don't panic, we're not going to integrate. Some of you are disappointed. Well, actually we are. I lied. Because the one force that we need to talk about that does vary, that we're going to use a lot moving forward, is the force that a spring exerts on something. This thing in the box is called Hooke's law. Hookes. Hookes. Robert Hooke. And it's a statement that says that the force of a spring depends on how much it's stretched or compressed. Okay? And you might see that, you'll probably see it written like this. Okay? But do you notice how mine doesn't have vector signs on it? Okay? That's for reasons that will become clear later. Okay? But if the vector signs are on it, there is a negative sign in there. Meaning that if you take a spring and you pull on it, which way is the force of the spring on your hand? Backwards, right? You've pulled it, to, in this case, to the left. The force would be to the right. If you pull it to the right, if you pull it to the right, which way will the force be on you? To the left. A spring always exerts a force opposite the direction it was stretched. That's what that negative sign is in there to remind us of. Okay? So let's ignore the vector version for just a second, right? So what's the force that a spring is exerting when it's not stretched or compressed? It's zero. X is zero. It's not stretched or compressed. Force is zero. But as we pull it more and more and more, as X gets bigger and bigger and bigger, the force changes. That K sitting in the front is called the spring constant. And it tells you like how strong the spring is. So a slinky has a really small spring constant. It's pretty flexible. But like the spring on a car's suspension is really, really strong to hold up the weight of the car. It would have a really, really big spring constant. Jell-O has a really low spring constant. Kind of get the idea right there, right? It's measured in newtons per meter, right? And we use K for the symbol, which is unfortunate because we're going to use K for a lot of different things in this class. Anyway. All right, so we're going to integrate. We're going to find the work that a spring does. Okay? First, this is really our first integral in this class, isn't it? So disappointing for a calculus-based physics class, right? Don't worry. Those of you taking 4B, we make up for that deficit. Okay, so this is kx is the force, dx. Since I'm pulling in the same direction I'm like stretching this spring, okay? I'm not going to worry about vector directions. I dot I is just going to be, 1. And now we get to integrate. Well, the spring constant being a constant goes where? It goes outside. Okay? And then we have x dx. All right, all of you calculus nerds, x dx. That should have been an instant answer, by the way. X squared over 2. It's been too long, hasn't it? You're doing like some real nasty integrals if you're in like 5B at this point. 1/2 kx squared, right? Evaluated from x initial to x final, right? So we can do like 1/2 kx final squared minus 1/2 k x initial squared, right? That is the work, okay, that a spring will do when it's stretched between 2 points. Now, if the initial position of your spring is 0, if you start with it unstretched and you stretch it out or compress it, what will the total work then be? Well, x initial is 0, so that just leaves me 1/2 kx squared, right? So just to, as a singular example of how we can use calculus to add up all the little things a spring is doing as it changes its force as it gets pulled out, in the end, we don't need to do integrals because we know the work that a spring is going to do. Any spring, stretched or compressed, and it doesn't matter, it's squared, right? So it doesn't matter if x is positive or negative. The amount of work that spring is going to do will be 1/2 kx squared. We'll argue about whether it's positive or negative later. Let's do a quiz. I really don't have time to do it, but I'm going to do it anyway. I want to derive something for you. I'm in a derivation mood this morning. Okay. Actually, I want to do this because it's going to come back to something. It's not Gerson's fault. He did ask about kinematics, right? And I told him it would be coming back, so this is my promise fulfilled. But I do want to show you where something you've heard about a lot comes from. And it starts. To be clear, will I ever ask you to derive things on an exam? No, like you don't have to memorize derivation. Trick question. You do have to derive your equations every time you're doing a Newton's second law problem, right? Like you have to develop the equations. That's less of a derivation and more of a like application of Newton's second law. Okay. Do you remember this equation?
Yep.
Yeah.
No? Thank you for being honest. Right? Okay, that was the third equation from the toolbox. Remember that one? Okay. I'm going to solve this for acceleration. 2 delta x. So there it is. That's the acceleration, right? Solved for. No amazing things have happened yet, right? I've done algebra. And then there is Newton's second law, isn't there? Oh. Well, mass times acceleration. Now I know what the acceleration is. Right? Again, I've just brought I've brought unit 1 together with the first half of unit 2. I'm going to move the delta x over. I'm going to pull. I'm going to write this differently. The 2 is in the denominator. The m is up there. I'm going to pull the m's through. And I'm going to get an f delta x over here, aren't I? What's force times distance? It's work. What's 1/2 mv squared? It's kinetic energy. Huh? What? This work, force times distance, has brought about what? A change in motion, right? A difference between some starting thing and some ending thing that has m's and v squareds and 1/2 and stuff in it, right? We say kinetic energy is 1/2 mv squared. If you change the kinetic energy of an object, you need to do work to make that happen. Work is a change in kinetic energy. So, we're still at the stoplight, right? Okay, we're in our car. What's our kinetic energy when the light turns green? How fast are we going when the light turns green? 0. What's our kinetic energy? 0. Because why is it 0? We're not moving. Right? Now we move, right? We accelerate. We gain speed. Do we have kinetic energy now? Answer before I run into the wall. Yes. Okay. Some of you were like, don't. But now that we're moving, we have kinetic energy, right? Kinetic energy is 1/2 mv squared. Is your mass ever 0? No. Okay? Is 1/2 ever not 1/2? No. Really, the only thing that's changing here is speed, right? So if we go from a state where there's no speed and have a kinetic energy of 0 to another state where we have some speed and our kinetic energy is not 0, where did the energy come from? Work. Was force applied over a distance? Yeah. Right? The motor, the wheels, everything applied force to get the car to accelerate over a distance. Work was done. And work caused a change in kinetic energy. Is that a question? So, what are the units of kinetic energy? Joules. Right? There's an equal sign here, isn't there? Right? Work is in joules. Kinetic energy is in joules. Right? Work and energy share the same unit, and so they are kind of the same thing. Jerson.
So that is the same thing as that?
That and that. What are you talking about?
Sorry, KE equals 1/2 mv squared is the same as delta K.
Yeah, delta K is just final minus initial, right? I have a final kinetic energy, 1/2 mv squared, minus an initial, right, 1/2 mv naught squared, right? So, and this is kind of the key point, right? Work isn't energy. Otherwise, we would just call everything energy or everything work. Work and energy are related to each other because a change in energy was caused by work somehow, somewhere. Okay? You need forces to cause changes in energy. How do we know? What's hiding in work? Force, right? There needs to be displacement. There needs to be force for work to happen. But if work happens, then will the kinetic energy of an object change? Yes. Okay? How much kinetic energy does the ball have right now? 0. How do you know? Isn't this better? Right? Did it gain or lose kinetic energy? It gained. How do you know it gained? It moved. It got faster, right? What was the force that did the work? Gravity. Right? Gravity did work on the ball. Positive or negative work? It was positive work, wasn't it? The displacement and the force were both down. And was the change in energy positive or negative? It's positive. It has to be because the work was positive. It started with 0 and then gained some amount. And so this is a negative velocity. It's going down. V squared. Does it matter? Direction doesn't matter. I like this. I really like this. Really quickly here in the last 10 minutes is a concept called power. And I know what you're thinking, okay? Power is money. We're talking about mechanical power, okay? Right? So mechanical power, by definition, is the work divided by how long it took that work to happen. What are its units? It's a joule per second, right? Which you know as a different unit called the watt. Now, you've probably heard watts not in its mechanical sense, but in its electrical sense. Where have you heard watts before? Electronics, like the wattage of your phone charger, right? You only got 5-watt charger. I have a 60-watt charger. Great. Okay. What does that mean? Why is the number bigger better? More expensive. Charges faster? Why does it charge faster? A 60-watt charger is doing how many joules per second? 60, right? 60 joules per second of electrical energy in this case would be flowing into your phone. You'll do electrical energy in physics 4B. We're not going to handle it in this class, okay? But that's the idea, okay? So a watt is simply a joule per second. Now, in mechanical terms, we generally don't, in the United States especially, don't use watts. Like if we wanted to talk about the power output of a car's engine, for example, sorry about all the car references. I really need to come up with different analogies. You don't go to talk to a person, hey, how many watts does your engine have, right? What unit are you usually using? Horsepower. Okay, first question. What kind of horse? Anyway. No. It turns out that there is a definition. Okay? 1 horsepower is equivalent to 746 watts, which is equivalent to 550 foot-pounds per second. What the heck is a foot-pound? Okay, it is a torque. But in this context, what is a distance times a force? Work, right? And a second's a second, right? So a foot-pound per second is the stupid unit systems version of power, right? And 550 of them, for some reason, is called a horsepower. And if you do the conversion into the metric system of units, 746 watts. By the way, if you go to Europe, car manufacturers do give you the kilowatt rating of the engine. Every motorsport, anywhere, including the one here in America, you know what I'm talking about, where they always turn left, because apparently they can't go any other direction. All of them rate their engines in kilowatts. Even if they say horsepower to the rest of us. Internally, all their calculations are in kilowatts. Anyway, so that's power. There's another way to calculate power. Let's do it in red. Power, since it's work, and work is force times distance, right? I'll just use x as an example. Over time, what is a distance divided by a time? It's a velocity, isn't it? So another way to calculate power, is to take the force and dot it into the velocity. So in the two boxes, right, you've got ways to calculate power. Power in watts, right? Both of these will turn out to be watts. If you know the work and you knew how long it took, you got your power, right? If you knew how much power was being output by a motor and how long it was operating, could you find out how much work the motor was doing? Sure, right? It's just a matter of multiplying, right? So the pretty easy equations, and the idea is to capture, it's really the only, pun intended, it's really the only time that time will be involved in energy. Energy usually doesn't care anything about time, okay? And so this is the one way that we sneak time in. We talk about power. All right, I will see you, hopefully in Grass, but if not, I will see you next Tuesday. Have a good day and a fantastic weekend.